Hello, welcome back. And today we will be discussing matrix algebra solutions for linear systems. For today's video, we would be discussing two methods, and the first method is the Kramers rule. For this rule, we need the coefficient matrix and the constant matrix. For coefficient matrix, these are just the coefficients of x. These are the coefficients of y. The constant matrix, these are your constants. Now, in solving the variables, you would need to find the determinants of the coefficient matrix and the determinant of this one. This one is just the coefficient matrix, but we replace the values of the variable that we are looking for to the constant. So for example, we are looking here for the value x. So instead of using a1 and a2, we would place the constants. So c1 and c2, and just copy the values of other variables. And for here, the y, copy the values, the coefficients of x, and then copy the constants. This is what Kramers rule look like if we have three variables. Now on to our problem. Before solving, we need first to construct our constant and coefficient matrices. So A is equal to 2, 1, 1, negative 2, 5, negative 1, positive 1, negative 7, and then negative 3. Then our constant matrix is 0, 3, negative 7. The first step for Kramers rule is finding the determinant. So A is equal to 2, 1, 1, negative 2, 5, negative 1, 1, negative 7, negative 3. Since this is a 3 by 3 matrix, we can do diagonal multiplication. And in doing diagonal multiplication in 3 by 3 matrices, we copy the first two columns. Now we solve for the primary and secondary diagonals. So this is 2 times 5 times negative 3 is negative 30. This negative 2 times negative 7 is positive 14. 1 times 1 times negative 1 is negative 1. And then for the secondary diagonal, this is 1 times 5 times 1. This is positive 5. And then this is negative 14. And this is positive 6. Oh, this is positive 14. Sorry. And then we will subtract the sum of secondary diagonals to the sum of primary diagonals. So it would be negative 30 plus 14 plus negative 1 minus 5 plus 14 plus 6. So this is negative 17 minus 25. So your determinant is now negative 42. Oh, sorry, this should be negative 42. Now, for our second step, we would now solve for the variables. The first variable is A. So this is our formula. This is A, B, C. This is our constants. We would just copy the coefficient matrix, but instead of the coefficients of A, we would use the values of the constants. So it would be 0, 3, negative 7, negative 2, 5, -1, then 1, -7, then -3, all over -42. Then we would copy the first two columns since we would be doing diagonal multiplication here. For our primary, this would be 0, 0, plus this would be -98, plus this is -3, minus, sorry, let me fix that, minus -7 times 5 times 1, this is -35, then plus, this is 0, plus, this is +18, all over -42. Solving this, we would have -101 plus 17 all over -42, which is equal to -84 over -42. Simplifying, we will have 2. So this is now your first variable. Next, we would solve for b. This is the value of a. This is our constant. This is the value of c. We copy the first two columns and then solve for the primary and secondary diagonals. 2 times 3 times -3, this would be -18, and then this is 0, and then this is -7 minus 3 plus 98 plus 0 all over -42. So this is equal to -25 minus 101 all over -42, which is equal to -126 all over -42, or simply 3. So this is your b value. Lastly, for y, here we perform diagonal multiplication again, so copy the first two columns. So this would be -70 plus -6 plus 0 minus 0 plus -6 plus 14 all over -42. Simplifying, this would be -76 minus 8, -42 is equals to -84 all over -42 is equal to 2. Now this is your C value. So our values for A is 2, B is equals to 3, and C is equals to 2. And then our solution set could be written as 2, 3, 2. For the matrix inverse, X here represents all the variables. So X is equals to the inverse of A times C, or the constant matrix, and inverse of A is equal to the adjoint of A over the determinant of A, which is the same as 1 over determinant of A times the adjoint of A. Similar to the Kramers rule, our first step is to find the determinant. Since we're going to use the same problem as before, we already know the determinant, which is -42. So moving on, we now find the cofactor of A. So this would be equal to M11, M12, M13, M21, M22, M23, M31, M32, M33. Using the array of signs, we know that these elements are the negative. Now we solve, since this is 1, 1, we cover or hide the and um, first row and first column. So what we would be left with is 5, -1, -7, and then -3. Then this one is 1, 1, -7, -3. And this is 1, 1, 5, -1. And this is -2, -1, 1, -3. Let me erase that. Then this is 2, 1, 1, -3. And this is 2, 1, -2, -1. And this is -2, 5, 1, -7. This is 2, 1, 1, -7. Don't forget the negative value. And then 2, 1, -2, 5. And now we solve. This is equal to 5 times -3 is equal to -15 minus -1 times -7 is 7. And then this is -3 times 1 is -3 minus -7 or plus 7. And then this is -1 minus 5. And 6 plus 1, -6 minus 1, negative, plus -2 plus 2. 14 minus 5, the negative of -14 minus 1, and lastly 10 plus 2. Solving this, we would have -15 minus 7 is -22. This would be -4. This is -6, -7, -7, 0, 9, and then this is 15, this is 12. Now this is now our cofactor of A. Moving on, we need to find the adjoint. In finding the adjoint, we just make the rows become the column and the column become the rows. So for the first row, -2, -4, -6, and the second row would be like this, and the last row is this. After finding the adjoint, we move on to our third step, which is finding the inverse of the coefficient matrix, which is equal to 1 all over determinant times the adjoint. This would be 1 all over -42. Then copy our adjoint, so it's -22, -4, -6, -7, -7, 0, 9, 15, 12. So this is going to be -22 over -42. This is -7 over -42, 9 all over -42, -4, -42, -7 over -42, 15, -42, -6 over -42, 0, -42, then 12, -42. Simplifying these fractions, we would have 11 over 21. And this is 1 over 6. This is -3 all over 14. 3 over 14. This is 2 over 21. This is 1 over 6. This is negative 5 over 14. This is 1 over 7. This is 0. This is negative 2 all over 7. So this is the inverse of A. After finding the inverse, we move on now to our fourth and last step, which is finding the values of the variables. So the formula is x is equals to inverse of A times C, which is the constant matrix. For here, we would perform matrix multiplication to these two matrices. So it would look like A11, A21, A31, or this. So it would be equal to 11 over 21 times 0 is 0, plus 1 over 6 times 3 is 1 half, plus negative 3 over 14 times negative 7 is 3 over 2. Now for the second row, 2 times 21, 2 over 21 times 0 is 0, plus 1 over 6 times 3 is equals to 1 half, plus negative 5 over 14 times negative 7 is 5 all over 2. And then lastly, the third row, 1/7 times 0 is 0, plus 0 times 3 is 3, plus negative 2 over 7 times negative 7 is simply 2. Adding these values, you would have 1 half plus 3 halves is 4 halves for 2. 1 halves plus 5 halves is 6 halves for 3. Oh, this should be 0. Sorry. So the last element is 2. These are now the values for A, B, and C, which is exactly what we got from the Kramers rule. And then our solution set is 2, 3, 2. So this is a summary that I created to show the different steps for each methods. This is not the formal definition or the formal way to show how to use each method, but these are the steps that I used in solving the problems earlier. As you can see, the Kramers rule involves two steps, which are finding the determinant and solving for the variables, while the matrix inverse involves four steps, which are finding the determinant, the cofactor, adjoint, inverse, and lastly, solving for the variables. So that is all for this video, Matrix Algebra Solutions of Linear Systems. Thank you for watching and good luck to your exams.